Hi, welcome to Coding Bootcamp's YouTube channel. Subscribe now and join our live stream session later. See you.
Good day, and welcome to this presentation of Introduction to Database Design. This course is a presentation of coding boot camps. There are no prerequisites for this course. This is session 1, before the advent of database systems. So session 1 we'll cover the file-based approach, and we'll also discuss the database approach. So with a file-based system, data was actually kept in files, and files are sections of memory that contain usually a mixture of ASCII and binary data. So the file-based system was one way to keep information on the computer and store it in permanent files, and applications would open these files, either iterate through or directly access the data. The disadvantages were data redundancy. File applications are created by different programmers in various departments, and after long periods of time, there could be drift with the configuration, so inconsistent data format. The same information is kept in several different places, so it was not a centrally located type of system. Also, again, data inconsistency, which usually stems from various copies of the same data in different places, conflicting, and wasted storage space and duplication of effort. Also, data isolation. It's very difficult for new applications to retrieve the appropriate data, which might be stored in various files that are not really documented. And also integrity problems. Data values must satisfy certain consistency restraints and constraints. So it's hard to constrain data within a file because it was almost always just text data. So converting dates or converting numbers was there was a big disadvantage as far as managing that data. It's also difficult to add and change the programs to enforce new data constraints with a file-based approach. And also security problems. Individual files are very hard to secure. Accessing privileges were inconsistent. Applications needed to have their access updated, and it was always difficult to enforce. And then there was always concurrent access anomalies, so data may be accessed by many applications that have not been coordinated previously. So the data file resources can actually be locked by one application, which means the other applications either will be in a race condition, or it'll just return an error. The application will return an error because the file resource is locked. So the database approach was a big advance. Database technology plays and still plays an important role in social media areas, also business, education, medicine. And to understand the fundamentals of a database system, we start from introducing the basic concepts. So a database is, by the broadest definition, a repository of data. We think of relational database systems as a database, or database management systems as databases, and that's true. But if we expand the definition, a file can still be a database. But a database is a shared collections of related data which is used to support the activities of a particular organization or to achieve a particular goal. A database can be viewed, again, as a repository of data that is defined and then accessed by various users. So the meaning of data. So data is factual information, such as measurements, statistics, names, attributes. We use data for discussions or as part of a calculation. And Data can define a person, a place, an event, an action, or just about anything. Usually when we set up a database, we model some kind of an object that we want to track. So a person, a student, a customer, we model the data attributes that we need to track or calculate or operate on that entity. So a single fact is an element of data or a data element. Welcome to video 2, session 2, where we will discuss what is a database and, more importantly, a database management system. Because when we think of a database management system, that's often confused with a database. So a database will have the following properties. It is a representation of some aspect of the real world. So typically with a database, we look to model real world objects. So it's a collection of data elements or facts representing some real world entities, but it's a model, and a model is always a simplification. So it's just some items, some attributes of that real world entity. We can think of employee. Employee, we don't model everything in our database for our application. We just might have name, social security number, address, and so on. So a database is a logical, coherent, and internally consistent repository of data. A database is designed, built, and populated with specific data for the purpose of modeling those entities, entering the data, and also retrieving the data. Here is a typical representation of what we call a database management system. A database management system is an application or a tool that is able to run many different databases. So we can have a database for application 1, program 1, where there is specific data and specific, in many cases, data tables that manage different real-world entities. Application 2, same thing. It may need different data. It may run for a completely different purpose. Application 1 may track customers. Application 2 may track employees. Application 3 may track products. So they can be completely independent, not accessible between the others, but it is a consistent repository of databases. So for management purposes and maintenance purposes, they are all under one single database management system that allows an enterprise to better manage its data. And again, we see here illustrated a little clearer our database management system. So we have our personnel, we have our accounting department, and our loan department. And the database management system is able to manage different databases for these different departments. And there are going to be different entities that will be tracked within different databases within the database management systems. So we can see here employees, checking accounts, saving accounts, loans, other data files are all managed either separately or all together. It would be hard to manage the databases all together because it would tend to get a little disorganized. However, it could be done. It's all going to be up to how the database administrator looks to manage the database. Again, it can be one large database to manage all applications, but that can be a bit of a big job. So usually the best practice is to break down the database management into smaller databases and almost always align the databases with individual applications. Welcome to video 3, session 3, the characteristics and benefits of a database. So Why databases? So we need to access data, and quite often resort to data for various uses. We may have to sort it, we may have to process it, and we need to create mailing lists, we need to capture information, we need to write reports, generate certain lists, identify various client needs. These are examples of reasons why we want to use a very specific and organized database. The processing power of a database allows it to manipulate the data it manages. So it can easily sort, manage, link, match, aggregate, skip fields, calculate, arrange. Most databases, most relational databases are very flexible in their queries. So in order to extract the data we need, most databases give us a very powerful query system that allows us to shape the data in almost any way that we need it. Because of the versatility of databases, we find them powering all sorts of projects and applications. Databases are the backbone, typically, of a website. We may hear the term web server. Interestingly enough, nothing is ever stored on the web server. The web server is runtime only. All data is saved on the database. So if we want any kind of client tracking application, social media, medical records, personnel and personal address for email, a collection of word process documents, or a system that issues airline reservations, are all powered by different databases. And the characteristic of a database approach, a database system contains not only the database itself, but also descriptions of the data and constraints. This is often called metadata. So metadata typically can be defined as attributes. So an employee and the employee's address. So the address is an attribute of the employee. Sometimes you hear metadata described as data about data, and well, that is true, but quite often it's better to have an example. And this information is used by the DBMS product or the database users if needed. So essentially, we can look up the metadata about the different entities that we're tracking in the database. So this separation makes the database system totally different from the traditional file-based systems in which data definition was part of the application program. And there is an insulation between the program and the data. In a file-based system, the structure of the data files is defined in all of the application programs. So if a user wants to change the structure of a file, all the programs that access those files may need to be updated. On the other hand, in the database approach, we use a structured or a data structured way to store it as a system catalog. That way, all programs will still access the data in the same way in which they were configured to access the data. And for the characteristics of the database approach, they can support multiple views of data. So a view is a subset of data which is defined as dedicated for a particular use or users in the system. So a view could be something as simple as the results of a query. Multiple users in the system might have different views of the data in the system. And hence our query example, not every user is going to see that result set. Each view might contain only the interested data of the user or the group that's accessing that data. Absolutely true. And then sharing of the data with a multi-user system. A multi-user database system must allow multiple users to access the data at the same time. as a result, the multi-user DBMS might have or must have the concurrency to
Thanks for watching. Feel free to add your questions as comments down below.
Control strategies to ensure that several connections can be made to access the data at the same time. And there are all kinds of strategies to optimize the database, including a replicated database system where there is one read-write node, we'll call it a node for right now, and then it's coupled with a group of read-only databases that are exact replicas. This optimizes the load and performance of the database system. And benefits to the database approach to control data redundancy. So in the database approach, ideally each data item is stored only in one place. However, in some cases, redundancy still exists to improve system performance, but such redundancy is controlled and kept to a minimum. That's like that example we just discussed, where we use database replication, and that's often a feature with most database systems, or it can be an add-on, where a replica is created and is constantly updated with the read-write node or the master node. Also, data sharing. The integration of the whole data management in the organization leads to the ability to produce more information from the given amount of data. And really, when we share data and we're able to view that data differently, it does result in an enhanced amount of information sharing or information gathering for the same data. And databases also enforce integrity constraints. So databases can enforce types, so integers, dates. So that way, no corrupted data can be entered into the database. And also, databases have user access. So we can control who has access to the system, who can read the system, and who can write to the system. So DBMSs should provide a security subsystem to create and control user accounts. And when we say control user accounts, we mean role-based type of accounts. So who can read data, who can write data, who can update data, and who can delete data. And also data independence. So the system data descriptions are separate from the application programs. They're almost layered on a different tier. So changes to the data structure is handled by the DBMS and not the embedded program. So again, this allows that independence. So any application can use standard ways to access that database. And also transaction processing. The DBMS or database management system must include a concurrency control system to ensure that several users trying to update the same data do it in a controlled manner so that the result of the updates is correct. So databases have a way of actually locking the data so a transaction can be completed by one user before the next transaction is started by the next user. Also providing, again, the multiple views of the data. So a view is a subset of the database. Various users may have different views of the database or the data itself, and users may not need to be aware of the way that the data is stored and referred to. So a query, a result set, sometimes an update, these are all examples of different views of the data. And then also providing a backup. In the event that the host fails, the hardware fails, that data must be recoverable, and it must be stored in a place where it can be easily recovered and again restored to online processing. Welcome to video 4, session 4. So here we'll discuss a high-level conceptual data models and record-based logical data models. So a data model is, well, just like this, the name implies, it is a model of the system or the business that we are trying to track. So it's just like all models are simplifications, it's a way of simplifying the entities and just capturing the data that we need. So a data model is a collection of the concepts in the data that can be used to describe the entity and build it into the structure of the database. And the structure of the database means the database types, the relationships, and the constraints. In addition, most data models include a set of basic operations for specifying retrievals and modifications on the database. So a data model also provides a way to achieve data abstraction. So data abstraction refers to hiding certain details of how the data are stored and maintained. With several levels of abstraction, the user's view of the database is simplified and leads to an improved understanding of the data. In other words, we can also state this as shielding the user from the technical details of the data. We discuss data abstraction in depth in the next session. So let's discuss types of data models, the high-level conceptual data models and record-based logical data models. So a high-level conceptual data models provide concepts that are close to the way that people perceive the data and to present the data. So a typical example of this type is entity relationship model, in which the main concepts of entities and attributes of and real-world objects and how they relate to other objects. So it's again, what is the business process for this data application? So an entity represents a real-world object, such as a customer or employee, for a project, and an entity has some attributes like name, like address, and they represent specific properties of the entity, again, such as name, address, birth date. And a relationship represents an association amongst the other entities within the application, so between the employer and the employee. Types of data models. So there's record-based logical data models, and that can be understood by the user, but it's not too far from the way data is stored on the computer. So three well-known data models of this type are the relational data model, the network data model, and the hierarchical data model. So if we look here, types of data models, we'll discuss each type in depth in the next session, but we can see here a logical data model, physical data. Physical data is the actual text data you see when viewing a database. We can see here the object-based, the record-based. So we can see here the object-based is modeling and is based on an approach, whereas here we are looking at the methods for modeling the data. And the types of data models. So for more details, please consult your course materials. And here is an example of the hierarchical data tree. So we have here a college, department, infrastructure, courses, teachers. So these could be different databases. They could be different data tables. Typically, though, we don't even know that. We just want to, number one, capture the organizations first, the business interaction. This way, we at least know the type of data we need. This is really why we want to model data, because we want to be sure that we know the type of data that we'll need. Welcome to this video, video 5, session 5. In this video, we will discuss degrees of data abstraction layers, schemas, logical and physical data independence. So there are 3 levels of abstraction. There is the view level. We've already talked about this. This is really the results or the result set that a user would get back from the data. It could be a listing of the whole table. It could be a filtered listing of only data that the customer is interested in. The logical level describes what data is stored as a whole in the database. And the physical level, that is the lowest level of abstraction, describes how the data is actually stored. So you can talk about hardware and software at this level. And again, the 3-level architecture here, or 3-layer architecture, we have our end users with their particular views. And a view means what data do you see, or what data comes back to the user in a result set. Again, here is our conceptual mapping here. So here we talk about how the data is actually stored and managed. And then we have our internal physical level that actually describes or gives a direction to how the data is actually managed on the host. So we can see from the picture in the previous slide, there are 3 levels of schemas in a database. And schema is an overused term, so we'll try to define it as we move forward. Typically, schema means template whenever we talk about a database. So the external level is the highest level. There exist a number of views which, if we define them, they are bringing back the data that's actually part of the data that's managed in the database. And each view is provided for a user or a group of users, so that helps it in the simplified interaction between the user and the system. So essentially, the best practice would be that there is some kind of intuitive interface that allows users to enter data and retrieve data. So an example would be the user fills out a form online, name, address, and other relevant information, and then clicks submit. And that's how the user would be interacting with the database. Then there's the conceptual level schema, and that describes the logical structure of the whole database. Here, we actually want to template the data. So the tables, the columns, the relations, so the entire database is described using simple logical concepts such as objects, their properties, and their relationships. Thus, the complexity and implementation detail of the data will be hidden from the users. So the users are shielded from all of the technical details of the system. And then the internal level is the internal schema, and it describes how the data are actually stored and how they're accessed. So there's different storage in a database. There is sometimes faster storage, faster memory. So that is all part of the internal schema. At the internal level, the 3 best known models of this kind are the relational data model, the network data model, and the hierarchical data model. So the internal models here consider a database as a collection of fixed sized records. They are closer to the physical level or a file structure. Are represented of the database as seen by the DBMS, require the designer to match the concept model's characteristics and constraints to those of the selected implementation model, and involve mapping the entities in the conceptual model to the tables in the relational model. And here we can see an example of a relational schema here. So there is an EMP here, or short for employee, that's capturing employee name and salary. There are managers here, and we can see here departments, suppliers, and we can see here the entity, or eventually these will become tables, and the attributes that go along with the entity. So we have employees, and we need the employee name and their salaries. We have a manager table, and we need those manager names. We have a works in table, and we need those names and department names. We see here there's a department name, and if you look closely here, you can actually see how the
If you have enjoyed watching this video, please subscribe to our YouTube channel. Thank you.
the tables relate. You can see ename here in this table and ename here, and that gives us a link between these tables. We can see dname here as in department name, and you can also see dname here in the works and so you can see how these two tables are linked. So the relational schema gives us a way of not only defining the tables and the data that we need, but how they relate or link to one another. And this is the linking gives us the advantage. We don't have to duplicate data. If we need a department name for the works in, we don't have to re-input or duplicate that data. You can simply just look back to the departments table. And this figure shows a schema for the supermarket in a network model. So you can see here networking, how these entities would connect to one another. And you can see the entities and actions here, what kind of actions there are. And this, you can also glean how the entities relate to one another. And again, this gives us a model for the data we need and how they will interact. And somebody who knows the business can look at this and say, yes, that is correct. This is how our current business is working. So we can see here the data and the data flows. And in this figure shows the supermarket in a hierarchical tree, so we can get an idea of a better idea of how the data will flow within the business. So again, this is important too to understand, not only in how we want to build our data, but also in how the application that we will build works. And if we have that bottom-up type of model, it really helps to in the building of the application, and a customer can easily come in here and validate, yes, this is our current business organization. And physical models are the physical representation of the database, and they have the lowest levels of abstraction and are how the data is stored, how they deal with runtime performance, storage utilization and compression, file organization, and access methods, also data encryption, very, very important. They are the physical level managed by the operating system and the application. So the DBMS application provides the concepts that describe the details of how the data are stored in the computer's memory. And data independence. So data independence is the ability to modify the schema in one level without affecting the schema in a higher level. And there are two levels or two layers of data independence. Logical data independence is the ability to make a change in that conceptual schema without having to or causing a need to modify user views or an application program. And that's very powerful because we can make updates and then no other applications are affected. If any of you are developers, you don't want to have to recompile applications every time there is an update to a database. And their physical data independence is the ability to make a change in the internal schema without a cause or without having to modify the conceptual schema or any other application that's accessing that data. Welcome back to the session 6. This session will be divided up into 4 videos. This is the first of the 4. The 4 videos will include classification based on data model, classification based on user numbers, classification based on database distribution, and distributed database systems. So let's first discuss database language. So there is a language called SQL, or Structured Query Language, and that is a standard for database access, relational database access. And structured query language, or SQL, can be broken into two sections. There is data manipulation language, known as DML, and this is used to define the conceptual and internal schemas for a database system. So this is where we create the tables, create the columns, drop columns. It is not a procedural language, but rather a language for describing the types of entities, just like tables we just talked about, and relationships. And we can link the tables through columns, so we said create column. So the types of entities and relationships among the schema in terms of a particular data model. So we can implement a data model using DML. And then there's data definition language, or DDL, and this is used to manipulate the database, which typically includes retrievals or insertions of data, and even deletions of data or modifications of data. So the DDL, that's the select statements, the update statements, the insert statements, and also the delete statements. And classification of database systems. So this is the data model. The most popular data model in today's commercial DBMSs is the relational data model, no question about it, although there are what we call NoSQL models as well, or NoSQL databases. The well-known DBMSs like Oracle, Microsoft SQL Server, DB2, MySQL, all support the relational database model. Other traditional models can be named. There is the hierarchical data model, the network data model, and also we are getting familiar with object-oriented data models. So some examples include the object-oriented DBMSs, O2, Object Store, or Jasmine. Welcome back to this video. This is video 7. We are still on section 6. In this video, we will talk about database classification based on user numbers. So we can classify our database system or how it is built or designed based on the number of users, where the number of users can be a single user, which would be a rather simple design, and where we could support either one user at a time or multiple users or multiple systems which support multiple users concurrently. The users do not have to be people or humans. The users can be systems as well, other systems, other processes. So this should be known when the database is designed, how it will be accessed, what kind of security will be needed, what kind of performance will be needed. A small number of users obviously can be a less complex type of design, but as there are multi users or multi-system users, the design will grow in complexity, such as growing horizontally, where database replicas can be added. We mentioned that earlier. That's considered a horizontal type of growth. There can also be what we call vertical types of growth, where more memory is added, faster disks are added. So those are the different ways to design a system based on the number of users. Welcome back to video 8. We are still on session 6, and in this session we are going to discuss classification based on database distribution. So there are really two types of distribution for a database. There is a centralized distribution model or a fully distributed database model. With a centralized database system, data is on a single site, usually a single node or grouping of nodes, and all of that, the design or all of the nodes are centrally located in one place. So if we look at this model here, we can see the central computer, the central host or the central node where the data is managed, and this icon here typically represents a database. You can see some kind of a client here where the application or the DBMS application is actually accessed. And then we can see the workstations, nodes, or terminals that actually access this data either through applications or through some types of reports. We can also see that this potentially could have some vulnerabilities, because if there was anything that brought this site down, all of the applications would be down. Welcome back, everybody, to this video. This is video 9. We are still in session 6, and in this video we are going to discuss fully distributed database systems. So databases can be classified again by their distribution, and here we are going to discuss fully distributed database systems where the actual database and DBMS software are distributed physically in various sites and connected by a computer network. They can be broken down into two parts. There is the homogeneous distributed database systems. They use the same DBMS software at the multiple sites, and data exchange between the various sites can be handled easily. So it's almost like the same database but with different components at different sites. And then there is the heterogeneous distributed database systems. These are different sites that might use different DBMS software. There are certain software products that support the data exchange and sometimes the data translation between these sites. And here we can see an example of the various sites and the nodes and how they will communicate over the network. Different topologies can be set up, and the nodes can communicate. Typically, it's the database node that needs to communicate with the other database node in order to deliver the required data back to the client. However, with these types of systems, there could be times where the application is able to do some direct access between nodes. So there is a lot of thought, there is a lot of design that needs to go into distributed database systems in order to optimize it. Welcome to this video, video 10. In this video, we are going to discuss fundamental concepts in the relational data model and the properties of a table. We are in session 7. So a relation, also known as a table or file, is a subset of the Cartesian product of a list of domains characterized by name. So quite often a table is an actor or an entity within the enterprise. And within a table, each row represents a group of related data values. So a row or a record, also known as a tuple or an instance, that if you're familiar at all with a spreadsheet, an Excel spreadsheet or any type of a spreadsheet, you're familiar with a table. You have the rows and you have columns. Columns in a table are a field, or also known as a field, and are often referred to as an attribute. So it's some kind of additional data that describes that entity. And you can also think of it in this way: an attribute is used to define the record, and a record contains a set of attributes. So the properties of a table has a name that's distinct from all other tables in the database. It's some kind of an entity in the enterprise, so we can't have duplicates of those entities. We would group those together if that were the case. There are no duplicates within each row. Each row is distinct, or each record is distinct. Why would we have duplicate rows? That wouldn't really add anything to the data model or to the enterprise. Entries in columns are atomic, meaning they can't be broken down any further. The table does not contain any repeating groups or multi-valued attributes. If we need to add other attributes, we add other columns. Entries from columns are from the same domain based on their data type, including numeric and...
Thanks for watching. Please like and share this video.
With this, we could have integers, floating, small ints, large ints, character, meaning a string, date, or some kind of Boolean or logical, true or false. So these are all the data types. And there can be others that appear in a column, and every column has its own distinct data type that goes for every record. Operations combining different data types are not allowed. However, there are data conversion functions. Each attribute has its own distinct name. The sequence of columns is insignificant, meaning the order that they are built in is insignificant because they can be brought back in a query in any order the user needs or the application needs. Also, the sequence of rows is insignificant. Rows can be sorted in any way that the application or that the user needs. And some key terms. Atomic value, each value in the domain is indivisible as far as the relational model is concerned. Attribute is a principal storage unit in the database and helps to describe the data in the table. A column contains attribute data. Degree, the number of attributes in the table. Domain is the original sets of atomic values used to model the data, a set of acceptable values that a column is allowed to contain. A field also is an attribute, and a record is an instance, and it contains all the fields for that table. And all records are unique. Welcome back to this video. This is video number 11 of our course, Introduction to Database Design. We are starting session 8. In session 8, we will discuss entities, entity sets, and entity types, kinds of entities, attributes and types of attributes, keys and types of keys, nulls, and relationships and relationship types. So in ER modeling, it's based on two specific concepts. So entities. Entities are real-world objects, usually nouns. There could be exceptions to that. They will ultimately define the tables that hold the specific information for our database. Relationships are defined as the associations or the interaction between the entities. So let's discuss entities, entity sets, and entity types. So an entity is an object in the real world with an independent existence that can be differentiated from other objects. An entity might be an object with a physical existence, such as a lecturer, a student, a car, or an object with a conceptual existence, such as a course, a job, or a position. You can think of them as tangible and intangible. Entities can be classified by their strength. An entity is considered weak if there is a dependent upon some other type of existence. That is, the entity cannot exist without a relationship to another entity. Its primary key, again, that is the attribute that makes a record unique. The primary key is derived from some kind of a parent entity. So take, for example, the spouse table in a database. The spouse table in a company database is a weak entity because its primary key is dependent upon the company employee or the employee table. Without a correspondence to the employee record, the spouse record would not exist. An entity is considered strong if it can exist apart from all its related entities. Kernels are strong entities. A table without a foreign key or a table that contains a foreign key that can contain nulls is considered a strong entity. Another term to know is entity type, which defines a collection of similar entities. And again, a foreign key is a primary key from another table that exists in a table, and it is actually a link to another table. So we don't have to duplicate the data from the other table. Another term to know is entity type, which defines a collection of similar entities. An entity set is a collection of entities of an entity type at a particular point in time. In an entity relationship diagram, an entity type is represented by a name on a box. So an ER diagram captures all of our entities and their relationships, so we can validate the business process for the application we're building or the value stream we are trying to automate, or just in our database reports. It basically validates that we have the data that we need. Welcome back to this video. This is video 12. We are still in session 8. In this video, we will discuss kinds of entities. So you should be familiar with different kinds of entities, including independent entities, dependent entities, and characteristic entities. So independent entities, also referred to as kernels, are the backbone of the database. They are what other tables are based on. Kernels have the following characteristics. They are the building blocks of a database. The primary key may be simple or composite, so meaning here the primary key is one attribute. A composite is the primary key is literally two or more attributes. The primary key is not a foreign key, so that primary key is not a link back to another table, and the independent entities do not depend on any other entity for their existence. Dependent entities, also referred to as derived entities, depend on other tables for their meaning. These are entities that have the following characteristics. Dependent entities are used to connect two kernels together. They are said to be existence dependent with two or more tables. Many-to-many relationships become associative tables with at least two foreign keys. They may contain other attributes. The foreign key identifies each associated table. And there are three options for the primary key. Again, a composite of foreign keys of associated tables, if unique, and right there that's telling you that there is a dependency or a link to another table. Use a composite of foreign keys and a qualifying column. Create a new simple primary key. Now, none of these are bad practice at all. It's just simply a way to define or associate your entities. For whatever reason, it may be a good practice to understand which are the dependent entities and understand those dependent entities when you are validating your data. But this is not at all to say that dependent entities are in any way bad. You need to model your enterprise as it is. And characteristic entities. So characteristic entities provide more information about another table. These entities have the following characteristics. They represent multi-valued attributes, so they're columns with multi-value attributes. They describe other entities. They have typically a one-to-many relationship. The foreign key is used to further qualify the characterized table. And primary key options are as follows. Again, a composite foreign key plus a qualifying column. Create a new simple primary key in the company database. These might include employee with employee ID as the primary key, and here are the other attributes. Employee phone, and notice here we have employee ID and phone. EID is part of a composite primary key here, so these two together denote the primary key. And here, notice that the EID is also pointing back or a link back to the employee table. So we can get the phone information, but we can also get name, address, age. There's no need to reproduce the data from employee in employee phone. Welcome back to this video. This is video 13 of our course, Introduction to Database Design. We are still in session 8. In this video, we are going to discuss attributes and types of attributes. So an attribute, sometimes it's referred to as metadata, it's additional data about a particular entity. It could be maybe for a customer table, could be customer address. That would be an attribute. There are simple attributes, and customer address may be a simple attribute. It's just one column. Then there are composite attributes. That's where we take two or more columns and combine them together for some kind of search or uniqueness. There are also multi-valued attributes. That would be in the case, say, selling in world markets. Many markets can be true at one time. There can be a North American market, European market, Asian market, and all of those attributes could be true at any given time. And then there are derived attributes, and that could be, an example of that could be converting temperature from degrees Fahrenheit to degrees Celsius. Welcome back to this video. This is video 14. We are still in session 8. In this video, we will discuss keys and types of keys. So a candidate key is a key in a database, an attribute that can define uniqueness. It is not a primary key. The best types of candidate keys are not repeated, but they certainly can. And a table can have more than one candidate key. A composite key and candidate keys could be related, and often are, because when we define a composite key, we are essentially enforcing uniqueness with two or more columns or two or more keys. So we could have a customer number and name together make a unique record. A primary key, whether it's composite or whether it's just singular or a simple key, does enforce uniqueness for that record. An alternate key, similar to a candidate key, also can define uniqueness, usually with in a composite type of arrangement. And again, tables can have more than one alternate key. And a foreign key is the primary key from another table that's in our table, and it's a link back to that other table. It can be used to bring in data from that other table, and it saves us from having to duplicate the data in a table, and obviously maintaining that duplicate data. Duplicates are always overhead type of work, and it can be missed. Welcome back. This is video 15 of our course, Introduction to Database Design. We are still in session 8, and in this video we are going to discuss nulls in the database. So a null is a special symbol. It's independent of a data type. It means an unknown or inapplicable. It is not zero, blank, or white space. It means no data entry. Very important. So it's different from zero. It's different from white space. Sometimes white space can be accidentally or incorrectly referenced as null. That's not the case. There's white space entered into a record. The data there is white space. It is not null. Definitely means no data entry, not permitted for a primary key. Obviously, a null can not enforce uniqueness. It should be avoided in other attributes. If we model our data and we need this data, chances are we should get the data, but if it is truly null, then that's fine. It can represent an unknown attribute value, a known but missing attribute value, again, a not applicable condition, and it certainly can create some problems with mathematical functions such as count, average, and sum. So be very careful when you're using these functions. And it can create logical problems when relational tables are linked. So beware of nulls. They are a fact of life, but they they can cause issues in a database, so just understand what data is null and do your best to eliminate as many null fields as possible. Some examples here. So we are running this query and we're saying select all the employee numbers from the salary table where the job name column equals sales and commission is greater than 30,000.
Thanks for watching. Feel free to add your questions as comments down below.
Now we don't see the results set here, so it'll depend greatly on how the database is designed, but we got two records back, employee number E10 and E12. Doesn't mean though there are not nulls though. So anytime you have a greater than, it is certainly increases the possibility we can get nulls back. Same as down here, it looks like our results here are also came back. But then again, we have our greater than. Typically greater than, less than, those are operators that could increase our chances to bring back records that have null columns or null attributes in them. Again, there's nothing wrong with it, but that there's data that's not there, and data is always useful in business. Welcome back. This is video 16 of our course, Introduction to Database Design. We are still in session 8. In this video, we are going to discuss relationships and types of relationships. So entities and tables do relate with one another. There is the one-to-many relationship and also a one-to-one relationship between entities. So here are some examples here. We can see a one-to-one where in this case there's a customer ID and an order, and one customer ID has one order and the order has one customer ID. But then there is the one-to-many relationship where one customer ID can have many order IDs, but every order ID just has one customer ID. There's also a many-to-many relationship. That is where we have a join table and a foreign key is involved. So we can see here how the many-to-many manifests itself. A urinary relationship is when it's recursive. It's when a foreign key refers back to its own primary key, or there is a foreign key that references the primary key of the same table. And ternary key is when there are three entities involved. And we see that a lot when we're talking about a good example are schools. So we could have a course with many courses, and teachers can teach many courses, and courses can have many teachers. And the subject of these courses, a course can have many subjects and teachers can teach many subjects. So these are the special relationships between the table. Again, we determine this really through modeling our enterprise. We collaborate, or somehow we just know the enterprise, and then we're able to identify the relationships between the tables. And in pointing out things like many-to-many, then we will know if we will need to relate tables, so we'll know specifically if foreign keys are needed. That is one of the advantages to identifying the relationship between entities. Welcome back to this course. This course is Introduction to Database Design. This is video number 17, and we are currently covering session 9. In session 9, we will discuss domain integrity, enterprise constraints and business rules, and relationship types. So constraints sometimes come up as a topic which has a reputation for being a little confusing, but it's not really confusing at all. Constraints are an important feature in a relational data model. So a constraint is almost always enforced buy the database management product, and it has to do with the data that goes into a column. So the relational model supports the well-defined theory of constraints on attributes and tables. So what we're going to do is constrain attributes or columns to only accept certain types of data. This not only helps with the with how your database interacts and how it behaves as far as the modeled enterprise, but it also helps to have it run more efficient and have it be optimized, because certain data doesn't require the same memory as other data. So performance can also be optimized as well. So what we're looking to do is enforce that when dates are needed, that only date type of data can be entered into a column. When numeric data is needed, so data that we may operate on, do some arithmetic on, or some mathematical calculations, that only that data is in a column. And when text data is required. And there are certainly other types of data. So constraints are useful because they allow a designer to specify the semantics of a database. And again, constraints are the rules that enforce the DBMS to check that the data satisfies those semantics. So there are several kinds of integrities and constraints described below. So entity integrity, and here we're looking to ensure that is required that every table have a primary key, and this is a best practice, and most database products will enforce this. It is almost really impossible to have a functional database without at least one column as the primary key. And then there's referential integrity, and that requires that a foreign key must have a matching primary key, or it must be null. This constraint is specified between two tables, parent and child, and it maintains the correspondence between the rows in these tables. It means the reference from the row in one table to another must be valid. Welcome back to this video. This is video 18. We are still in session 9, and in this video we are going to discuss enterprise constraints and business rules. So enterprise constraints are sometimes referred to as semantic constraints, and they are additional rules specified by the enterprise. So they're really rules for the enterprise, and we get these rules from users, business analysts, or even database administrators, and they can be based on or enforced on multiple tables. So these are the rules of the enterprise that we look to model into our database. So here are some examples. A class can have a maximum of 30 students. So obviously there is a constraint there to limit the size of a class to 30. A teacher can teach a maximum of 4 classes per semester. So again, we see more of a business or an enterprise rule there, which we will build into our database and our application as well. An employee cannot take part in more than 5 projects. The salary of an employee cannot exceed the salary of the employee's manager. Again, these are business rules that we will build into and enforce through our application and database. And business rules are obtained from users when gathering requirements. The requirements gathering process is very important, and its results should be verified by the user before the database design is built. And these business rules also give us some valid business rules or just valid requirements to test against. So we have a good test case. If the business rules are incorrect, the design will be incorrect, and ultimately the application will not meet the expectations of the users. So some examples of business rules are, again, a teacher can teach many students, a class can have a maximum of 35, a course can be taught many times but only by one instructor, and not all instructors teach classes. So again, these are more examples of enterprise type rules and requirements that we look to implement through our application and database design. Welcome back to this video. This is video 19 of our course, Introduction to Database Design. In this video, we are going to discuss relationship types. So we're talking about relationship types. There are many instances of relationships, but they fall into these types here: optional relationships and mandatory relationships. So with an optional relationship, the two entities may or may not interact with one another. So they don't require participation from one another. So we can see here is an example: a project and a consultant. Not every project will have a consultant, and there may be times when a consultant doesn't have a project. And then there are mandatory relationships, and those are relationships where the two entities must participate or interact with one another. And here is an example: a barber and a customer. So when a customer gets his or her haircut, the barber must always be there. So in this case, it's a mandatory relationship for these two entities to participate. Welcome to this video. This is video 20 of our course, Introduction to Database Design. In this video, we are discussing session 10. And session 10, we will review relational database and redundancy, insertion anomaly, update anomaly, deletion anomaly, and how to avoid anomalies. So again, a little bit of a different context for business rules. One important theory developed for the entity relational or ER model involves the notion of functional dependency, or FD. Like constraints, functional dependencies are drawn from the semantics of the application domain or the enterprise. Essentially, functional dependencies describe how individual attributes are related. Functional dependencies are a kind of constraint among the attributes within a relation and contribute to a good relational schema design. So in this session, we will look at the basic theory and definition of functional dependency and the methodology for improving schema designs, also called normalization. So relational design and redundancy. So generally, a good relational database must capture all of the data necessary to model the business or model the process that we are trying to either automate or improve, or somehow create an application that supports the business. So we need to capture the necessary attributes and understand the associations. And we want to model that so we know how to properly build our application or our reports, whatever effort that we have underway. The design should do this with a minimal amount of stored information and no redundant data. We don't want any more data than what we need. We want only the data that models the enterprise. And obviously, we don't want redundant data because it can become inconsistent and it is extra data to maintain. And chances are, if the redundant data needs to be maintained, it will quickly become inconsistent. Welcome back to this video. This is video 21 of our Introduction to Database Design course. We are still in session 10, and in this video we are going to discuss the data insertion anomaly. So an insertion anomaly occurs when a user or an application is inserting data into a table with either null or inconsistent information, and an error is returned by the application. It's usually with very unclear next steps. If it's the case of a null, it becomes incumbent upon the user to research and get the data that cannot be null, or some other placeholder data must be inserted that makes it clear that it is a placeholder. Welcome back to our course. This is video 22 and we are still in session 10. In this video we are going to discuss the update anomaly. So similar to the insertion anomaly, an update anomaly occurs when there is an inability to modify or update the data in the database due to the absence of other data, like fields that...
If you have enjoyed watching this video, please subscribe to our YouTube channel. Thank you.
...that are not null, that must have data, and the update command does not contain that data. There can also be inconsistent data. Again, similar to the insertion anomaly, the next steps may be unclear coming back from the application or from the relational database management product, but typically it will be incumbent upon the user to either supply that required data or seek support for the error that is being returned by the product. Welcome back. This is video 23. We are still in session 10, and in this video we are going to look at the deletion anomaly and how to avoid anomalies. So with the deletion anomaly, a deletion anomaly occurs when a user attempts to delete a record that may contain attributes that shouldn't be deleted. It's possible that an error will be returned and the record will not be deleted. It also may be possible that the user believes the record is deleted and shouldn't be. Also, it may happen that the record is deleted when in fact it should not have been deleted. There are two responses in that case. If a record is deleted accidentally, it may be possible, if the database is not yet committed, to run what is called a rollback. A rollback will restore the database to the state that it was before the transaction. However, if the transaction is already committed, a rollback will not be possible. At that point, if the database is already committed and data is inadvertently deleted, the only option is to restore the database from backup. A great way of dealing with anomalies is to avoid anomalies, and the best approach is to create tables without anomalies and ensure that we use a process called normalization. And this is accomplished by understanding functional dependencies. It's almost like breaking our entities down into their simplest forms and validating the relationships. So FD ensures that all attributes in the table belong to that table, and we want to also eliminate redundancies, use foreign keys often and when needed, and also we want to validate that the tables are just atomic, broken down to their simplest form. It can result in having more tables than what the original estimate was, but this will be a great way to ensure that there will be as few anomalies as possible. Just to recap what we have covered, so we started off with before the advent of database systems. Then we looked at the database fundamental concepts, the characteristics and benefits of a database, the types of data models, and we looked at data modeling, classification of database management systems, the relational data model, the entity relationship data model, integrity rules and constraints, and entity relationship modeling, or ER modeling. Stay tuned for our next session where we will review some exercises. Please also consult your learning materials for private tutoring sessions covering database administration, and also private tutoring sessions for database design and structured query language coding or SQL coding. Some recommended next classes: Introduction to Structured Query Language Programming or SQL Programming, Introduction to the Linux Operating System, learning PHP programming, learning web development with PHP and MySQL, also learning Node.js and Express.js, and the MongoDB. Thank you for watching these sessions, watching these videos. Please stay tuned for our next videos where we will review the exercises. And again, this course has been a presentation of Coding Bootcamps. Welcome to this video where we will review exercise 1, and this is starting to build out the university registration data model. So what we want to do here is we want to take the simplified route. Obviously, a university registration data model can get quite extensive, but we want to just look at the basics for now. You can see here's a list of the entities. Here are the instructions here. And here are a list of attributes. So what we want to do here is list out at least 5 other additional entities and then fill in all of the attributes. Here is a start. So we have course, that's one entity. Course ID is an attribute, and course name is another attribute. So fill in the 2 additional attributes for course, and then list out what you might add for the entities for a university registration data model. Some are obvious, but possibly some are not. There is also a project document to take a look at. So after you've completed this exercise, go ahead and take a look at that and review it and see if what you can draw, what conclusions you can draw from what you did as far as the entities and the attributes and what's in that document. In this video, we will review what you should do for exercise 2. So take all of the entities that you listed in exercise 1 and use this template or the pattern here in this file. You can copy paste these boxes. You can copy paste this line here. Fill in the entity names, and you can just overtype this and fill in the relationships between your entities, and you can arrange these any way that you need. Don't worry about adding the attributes for now. You can certainly key in the attributes if you want to. If you need an example, page 2 has an example here. So the most important thing is arranging the entities, and the entities are the names up here at the top. You can list the attributes below certainly if you want to, but that is optional. And use the lines, and don't worry about the direction, just to identify the relationships. And then there is a document under Project 2. Take a look at that, see how that was done, and see if it is aligned with what you did, and what did you do different from it. End. Welcome back to this course, Introduction to Database Design, presented by Coding Bootcamps. This is a sample project, the ERD exercises, Entity Relationship Diagram exercises. So in this exercise, we are going to take a look at creating entity relationship models based on some criteria that were given. So we can see here in exercise 1, we have a manufacturer. And a manufacturing company produces products. The following product information is stored, so it's maintained in the system. We have the product name, product ID, and the quantity on hand. The products are made up of many components. Each component can be supplied by one or more suppliers. The following component information is kept: component ID, the name, the description, the suppliers, in that who supplies them, and the products in which they are used. And if we look at figure B for this exercise, we will create an ERD to show how you would track this information. So we want to show entities, the names, the primary keys, and the attribute for each of the entities, and the relationship between the entities, and also the cardinality. We went over cardinality in our course. The assumptions we're going to make: a supplier can exist without providing any components. A component does not have to be associated with a supplier. A component does not have to be associated with a product. Not all components are used in all products. And a product cannot exist without components. So these are the business rules that we have to establish. So these are these rules and these assumptions cannot happen on their own. So none of this is really database driven. These are actually rules that we are getting from the enterprise. These are rules that we have to implement in order to create our entity relationship diagram. So in order to successfully model an enterprise, we have to know the rules of the enterprise. So we want to discuss this with analysts. We want to discuss this with managers and possibly others that are involved in the process, in the business process we're trying to model. So as we move down here, we can see that first thing we are going to come up with our beginning our model for our components. So we'll have our component ID, our component name, and our component description. One thing that's very important, we have to understand, how do we keep each component identified uniquely? So we're going to call that our PK, or our primary key. So that's going to be our component ID. And that makes sense. That sounds very, very typical, a good practice approach. So we have our component ID, our component name, and our component description. That, for our purposes right now, is enough to describe a component. There could be more, but this is enough to get us out of the starting gate. So for a product, we are going to have a product ID, a product name, and quantity on hand. And a product is going to be unique in our system using product ID, so that'll be our primary key. Then we're also going to have supplier. And again, for us, we're going to have a supplier ID, a supplier name, and suppliers are going to be kept unique by using a supplier ID as our primary key. So we'll enlarge this a little bit, and then we'll move down here, and we can see we have two more entities. We have our component supplier with our component supplier ID and our supplier ID. And we can see here that we have a compound primary key, which is comp ID and supplier ID. And then we have build, which also has a component ID, a product ID, and a quantity of components. And we see here our primary key is also a compound primary key, where we have together component ID and product ID. So here we would use some tool. Maybe it is Visio. There are lots of tools on the market that help us build these entity relationship diagrams. But what we want to do is first put out our component, our supplier, and possibly product. So that's what we started with up here. And they were relatively simple. So again, we have component, we have the three attributes, and we have the primary key component ID. So here we have our component name, description, and we have identified here as our primary key, we have the component ID. Then over here, we have supplier. And we said with supplier, we have the two attributes, supplier ID and supplier name, and we have as the primary key, supplier ID. And for product, we have the three attributes. We have the product ID, product name, and quantity on hand. So we would build this right here. We have the appropriate product ID there. Then we said for component supplier, it would be a combination of component ID and supplier ID, and the two primary keys together, the compound primary key would be component ID and supplier ID, but also these would be foreign keys because the way that they relate. So notice this is relating right here based on supplier ID. And component ID is also relating here. So these foreign keys are primary keys in a different table. And we are actually able to bring in the supplier name because of the supplier ID. And from here, we are also able to bring in component name and description based on that relationship there. So we can see there how.
Thanks for watching. Please like and share this video.
These tables relate. And this is drawn in a way that that relationship is very clear. So this is a good drawing. And we can see here our build table also has our component ID, our product ID, and quantity of components. And this is pointing back to the product ID with its foreign key. And both of these together, these two keys together or attributes make up the primary key for this table. So we can see that there, but we can also see component ID is pointing back up here to the component table. So let's zoom out a little bit here again and try this on your own. Just sketch this up. You can pick a tool. It can be PowerPoint. It can be Visio. It can also be other tools that are out there. Usually tools that support ER diagrams or entity relationship modeling. There is a free version, so please do go out and take a look and think about what is involved in modeling the enterprise or the business unit for your application. Let's take a look at exercise 2. So exercise 2 here, again, they're giving us the business rules. So we have to model or create an ER diagram for a car dealership, and the dealership sells both new and used cars, so that's important, and it operates a service facility. And we want to base our design on these business rules. A salesperson may sell many cars, okay, so we're getting into cardinality here, but each car is sold by only one salesperson. And so that's important, that relationship. So each car has a salesperson, but a salesperson may have many cars. A customer may buy many cars, but each car is bought by one customer. So again, that's important. A salesperson writes an invoice for each of the car he or she sells. Customer gets an invoice for each car that he or she buys. A customer may come in to have his or her car serviced. That is, a customer need not buy a car to be classified a customer. Okay, and another important rule. These are all rules that are looking for a rather, I'm not going to say completely complex, but something a little more than simple cardinality model. When a customer takes one or more cars in for repair or service, one service ticket is written for each car, and a car dealership maintains a service history for each car that is serviced. These service records are referenced by the car's serial number. So maybe this is some uniqueness here we're getting. A car brought in for service may be worked on by many mechanics, and each mechanic may work on many cars. A car that is serviced may or may not need parts, adjusting a carburetor or cleaning a fuel injector nozzle may not require providing new parts. So this is just an example of servicing where new parts are not needed. Also possibly filling tires. If a tire is a little low, obviously we are not going to replace the tires in that case. So if we look here at the entity relationship model, we can begin to see here how it may break down. What we want to do, and let's zoom out just a little bit here so we can see it. Let's adjust. And so let's take a look here. So obviously we know we have the car. We know how to identify the car with the car primary ID. Let's take a look at the primary ID. So we have the car table. We determined we needed a car table. One of the things are we want to determine all of the entities. So we know we have a car. We know we have a sales invoice. We talked about that, a salesperson, the mechanic, the service ticket, the customer, service, parts used, and service mechanic. So that sounds like we covered all of the entities involved in this model. Now we have to, for each entity, take into account what the attributes are and also what the cardinality is. So we know for a car here the serial number, so we're going to have a car ID instead of a serial number for our primary key. We can see the PKs, the primary keys that were identified. It's an attribute, but it's a special attribute, as you know. Serial number, make, model, color, year, and car for sale, yes or no. So as we go through here, we want to think about these relationships. We already talked about that a sales invoice has one salesperson, so that's a one-to-one, but a salesperson can have many invoices. So we see here the one-to-many, that's right here. We also here, we're seeing that mechanic, in our mechanic ID, again, a mechanic can service many vehicles, but a vehicle is only going to be serviced by one mechanic. And we see here a service ticket, the one-to-one here. So we have to think about here, what are the possible cardinality, and this is again called cardinality. If we also said that a customer could buy many cars, so or could have many service tickets, and also this zero in here, a customer may not buy a car, so that's why it's zero to many, right? The customer may not buy a car because the customer may be there just for service, so that's why it's zero to many as far as cars to sales invoices. But a service ticket will always have at least one customer, and a customer may have zero to many service tickets. So this is a little more of a complex approach to putting together our entity relationship model. And I think the cardinality is going to be one of the trickier parts. But notice here there are also foreign keys. So as we put together our sales invoice, we want to look what are ways that we have to describe the sales invoice from other entities. And in this case, we can see we have the car ID, the customer ID, and the salesperson ID. And that makes sense. We have our sales invoice, and this is nicely placed right here so we can look back to the salesperson. So we see the primary key for the salesperson table here in the sales invoice. We have the car ID and also the customer ID. And one of the best uses for the foreign key, it definitely shows how they relate, how they link, but also we don't need all of this car ID information back in the sales invoice table. All we need is the car ID, and then we can bring in this information by simply querying the car table. And the same thing with the customer table, and the same thing with the salesperson table. And if we look over here too for the service mechanic ID, we can see we have the three foreign keys that we've identified. So we have the service ticket ID right here, and we have the service ID, and we also have the mechanic ID. So we're able to bring in all of this information from those tables. And likewise with the parts used, we're going back to the parts table. We're able to determine which part was used, and also the service ticket. Right, it's looking right back up here for the service ticket. So we've got to think about those relationships as we come down to our identities with our foreign keys. Those are the tables that will be relating, the ones with foreign keys, and those are the ones that we need to describe the relationship. So the foreign keys tell us how they relate. They also give us links back to the data So when we are running our application, or we are simply running reports. So take a look at this. Again, go through these rules, see what you come up with. Go into either Visio, go into PowerPoint, and do your best to mock these up. Don't look back too much to the answer. You can always have it to reference, but eventually a DBA can take this and very quickly move this into what we call a physical data model, and that physical data model will be the schema or the template for our database, and then that database can be used obviously for an application. Could be a web application, could be a mobile application, or some kind of report type of application, report on sales and so on. But please do take a look at this. And if we scroll down a little bit further, we can see here that the exercises are from a database design. So when you're done, take a look at that as well.